going to be what? 11. Value is going to be 11. Right? Now estimate this cost. So which is from S to A to C, C to G. S to A is 1, right? A to C is 1, right? And C to G is 4. Now what is G of N? G of N is 1 plus 1 plus 4, which is 6. 6 plus, what is the goal node? What is the node of G? What is the estimated cost of that? Which is nothing but H of N. What is H of N? Which is 0. So 6 plus 0 is going to give 6. Right? So now among the node which is already in the open list, you have to compare the value of f of n. So the value of this is going to be 11 and this is going to be 6. The node which is already there in the open list, which is having 7, and one more which is having 10. There are 4 nodes in the open list, right? So in this open list, which has the least f of n, you have to identify, right? So among 10 or 7 or 11 or 6, which has the least, which is has the least, 6 is having the least. And so now what is the node to be moved to the goal state? Is your G, right? So is G is your goal state? Yes, G is your goal state, right? So now we reach the goal state. Now what is the path we have been visited? We started from S, then we went to A, we went to C, we went to G, right? What is the total cost of that? The total cost of that is going to be S to A is 1 plus A to C value is 1 plus C to G value is 4, which is nothing but your 6. The path cost is going to be 6. Now, if you observe the other paths which we have in this is from S to G also. G is your goal node, right? From S to G, what is the cost of that? The cost of that is 10. Even we find the solution, but that is not an optimal solution, right? It is of 10. Now suppose if you reach via this to the goal node, what is the cost of this? 1, 1 plus 1, 2, 2 plus 3, 5, 5 plus 2, 7. To reach this goal node, which is of 7. We reach to goal node, this is of 6. And what is the value of this? Is 1 plus 2, 3, 3 plus 5, 8, 8 plus 2, 10 again. To reach this goal state is 10. So the path cost of this to reach the goal node is 10. To reach the path of this goal node is 10. To reach the path of this is 6. To reach this goal node via this path is 7. If you observe, we got a minimal cost, which is nothing but the optimal solution. This is where the A-star algorithm plays a vital role in the informed research, where it gives us a solution and we guarantee that it will be the optimal solution, right? Right. So if you observe, this is the iteration, how it is being happened, right? So where for each step what it is, it's having your f of n is directly given, right? So this is for your reference, but you have to make the iteration and finding for each node what will be the f of n, what is the g of n and h of n. So you have to calculate for every node f of n. F of n is equal to g of n plus h of n, right? And as I told you, this is going to be the final cost, which gives as the optimal cost, which is 6 among other solutions, right? So that is your A-star algorithm. So it can be used for finding the path also, right? So this is another example. So where this is a route map, right? So where they gave the error. So this is the example which has been from your textbook, right? So you can take any simple example, but as it is given in textbook, you have to know about how it works. So they have taken a part of it in which they said this error is the starting node and the destination of that is Bucharest, right? you have to find the optimal solution from the Arad to the Bucharest, right? So where it could be the optimal solution, right? So that is your starting node, and for each node the estimated cost to reach your goal node is being given, right, with h of n, because we need to know what is g of n and h of n, right? So we have multiple paths to reach the Bucharest, right? So from Arad you can come to Cebu, then Fagares, then to Bucharest, right? Or else you can come from Arad to Timisoara, then Lugoji, then Mahalia, then Norbeta, from Craiova, then Pitasti and Bucharest, right? Or else you can come via this route also and reach your Bucharest. There are multiple paths to reach the destination. Among this, which could be the optimal cost? Optimal cost is nothing but which gives the less cost to reach your destination, right? So that is where the A-star algorithm goes, right? So this is an example which is given. I will show you one which you have to do it further, right? Right, if you observe here, these are the heuristic value, which is nothing but a h of n, or for each node it is defined, right? So the first node will take the source node as the Arad, right? So which is having 366. So you need to draw So we'll take Arad, right? So and you have to consider that since that is the first node, so it is going to have the g of n as 0, right? And the h of n is going to be 366. So this will be the first which is going to be considered. And from Arad we are going to explore the node which is of its neighboring nodes, right? So we'll see how it is. Right, so this is the example. If you observe, this is where Arad is. The adjacent of the nodes which is called Cebu and Timisoara and Zirin as the nodes. So the first root node which I say is, since that doesn't have g of n, because that is the starting node, so that is 366. Now the node to be explored is these three nodes, and here the Cebu is having the path cost. You have to check what is the path cost of it. Right? So the path cost of this is 140 and path cost of Timisoara is 1180. Right? So these two costs, and Zerin is there, which is the path cost as 75. So along with that path cost, the heuristic value h of n is added, right? So you have to check what is the heuristic cost of this, right? So we need to know what is the heuristic cost of Cebu, we have to know about Timisoara, and we have to know about Zerin, right? So take those heuristic costs and add your f of n is equal to g of n plus h of n. So if you observe, we have calculated all the. Now which could be the next path which leads to the optimal solution is decided based on the less f of n. So which has the less f of n? Cebu is having the less f of n, which is 393, this is 447 and this is 449, right? So now what could be the next path we have to visit is your Cebu, right? So Cebu is being visited, and again you have to explore the neighboring routes, right? So this you have to continue, right? Take this as an example, evaluate and check the value of each nodes of f of n and which paths to be leads to the goal node. When you reach the Bucharest, then calculate the final cost of it, right? So you need to do this. So I will show you about the solution of this, how it is. So this is the final where we reach the Bucharest, right? So this is where from Arad to Bucharest is being reached, and the cost of this you need to be calculated, right? So this I am giving you for doing it, so you can evaluate that, right? So then when we talk about the properties, as we discussed in uninformed search, informed search also we have discussed these properties. So first talks about the completeness. Yes, it is complete until we don't have any infinite node, right? And the time space complexity is being given. So space complexity, when we talk about, as it is gives us the better space for it, whenever we find the heuristic value, the node is going to be saved in the memory, right? And it is going to have the better timing, right? So usually we will do for uninformed search is the order of B into D, right? So but here it is for the best case of H, because heuristic values plays the vital role, right? So if you have the heuristic value is perfect, then the best case for that will be order of D, right? And if it is optimal, yes, obviously it gives us the optimal solution, which is the less solution compared to other, right? So it is optimally efficient, right? So coming to the space complexity, as we know that it has to keep track of your parent node and the child of it, the final path has to be determined to reach your goal node, right? So it is going to be order of B to the power of 3, right? So why B, the depth, already we much enough discussed with the uninformed search, right? So the next is your local search. So this is why we call it as local search, is where the search is going to be providing the optimal solution by considering the current state. So as it is considered from the current state, we call this as the local search. So under this we will discuss about what is your hill climbing algorithm. So that is an informed search, but still we call it as local search, is where each stages is going to be observed from the current state, right? So they are going to keep only a small number of nodes in the memory, right? Instead of exploring all the nodes, it is going to keep only the smaller nodes, right? So which will lead to the optimal solution, right? So this is an optimization problem, right? So it finds the solution, right? But it is hard to find the best solution, right? But whatever the solution is going to derive will be optimal, right? It guarantees for the optimal. And how the local search is going to work? It is an iterative method, going to start with the solution and it improves towards a good solution, right? So this follows an iterative method in the local search, right? So what is hill climbing? So we know generally what is hill climbing, what is meant by hill. The hill is going to have a peak, right? So the top of the mountain is called as a peak. There can be some ridges, right? So there can be some flat land, right? So why we are talking about this is a value when we talk about in the hill climbing may vary from a stage to stage, right? So to determine that, they have defined the hill climbing, right? So where the it is compared with the mountain, so the value may be increasing or decreasing, can be same. This is nothing but a flat, right? So it is going to talk about the greedy local search. So why it is greedy is obviously choose the best solution, right? So it is also sometimes called as greedy local search, right? Because it is going to check the neighboring nodes, any neighboring nodes which is going to have the node which is least compared to the other nodes, right? So that is going to be the next path, right? So which will lead to the goal state. So in this hill climbing, right? So we perform quite well because it is going to be greedy, right? So which chooses the best solution, right? So what is that hill climbing is? The value may vary from uphill to the downhill, right? So the increasing of a value, and it terminates when it reaches to the peak, where no neighbor has a higher value than that. Right? So it may vary. We have various terminology which we have to understand in the hill climbing, right? And this is going to be the memory efficient way to solve the large computational problems, right? And as I told you, the hill climbing is going to consider the current state, which is going to be the immediate neighboring state, right? And this is going to be either maximize the value or minimize the value based on the function. So what are the problems, before going for problems, we'll see what are the key features of hill climbing. As I already told you, it is a greedy approach, right? So it is going to find the local maxima or minima. So what is the local maximum is talking about the value which is being nearest to the goal state, right? So the greedy approach talks that it goes in the direction of where it gives the local maxima or minima. And no backtracking in this. As I told you, hill climbing will work based on the current state, right? So there is no backtracking. So it need not to remember what is the previous state it is. And next is it is working based on the feedback mechanism. So the previous state's feedback will help us to choose the current state, right? So which will tell us how to decide the next actions to be, right? Whether we have to move up or down, right? The decision can be easily done based on the feedback mechanism. So these three are the important key features of hill climbing. So as I told you, this problem is being depicted with this hill climbing diagram, right? So which it can be an initial state, start from here. And if you see, there is a changes in the graph which we call it as shoulder. So sometimes where it comes to the value, right, suddenly if there is a rise in that, right. So if stabilize and then if it is rise, this is the shoulder, right, probably it will have the same value in all the stages. And here the peak we call it as a global maxima. So which gives us the higher value, right. Again, if you see, there is a drop in the graph. Again, there is one more peak which is called local maxima. So local maxima will have lesser value compared to the global maxima, right? So not all the times we will expect the global maxima. We will concentrate on the local maxima because the current state may leads to local maxima, right? And then we have another which is a flat. Right, so this is also a local maxima, but where the situation, if all the status gives the same value, now which to be chosen wisely matters there, right? So if the values are common in all the decisions in the current state, right? So now which to be chosen? So that is called as the flat, right? So when we talk about hill climbing, the changes of a value, right? So talking about this is where it talks about from initial state how it varies, right? So that is how it is named as hill climbing. It looks like a mountain hill, right? So where we can find ups, downs, there can be a peak, right? There can be another peak which is lesser than that, which has a greater value. There can be a flat, can be a shoulder or a flat, right? So what is local maxima is what I said, right? So it is a state which gives us a better neighboring state, right? So the best possible solution can be achieved, right? So wherever we set the objective value for it, right, that is going to be higher than that, right? And what is global maxima or minima? So this could be the possible state, right? But the objective function will be two highest. So when we talk about the highest value, it doesn't mean that will lead to the optimal solution, right? So preferably we will concentrate on local maxima than this. But a neighboring can have the highest value, that is there can be a global maxima or local maxima. In current state, we know that the state where currently the agent has to make a decision, right? So that is your current state, right? And flat, what is flat is where it depicts the straight line where all neighboring value is going to have same value. When you have same value, which path you are going to choose it, right? So we don't know which path is wise to choose the promising path, because if we have the lesser value, which is a local maximum compared to the neighboring node, then we choose the lesser value as the path to export further. But if it stays with all, that situation we call that as the flat. Next is your ridge. Ridge is where it is going to be higher than the neighbor, but itself has a slope, right? So ridge is going to have a slope. So it is a special kind of local maxima which can occur, right, in hill climbing. So there are some of the problems in hill climbing, right? So what it is a local maxima, ridge and plateau, which is nothing but the flat, right? So what we talk about the local maxima, when you consider that, right? So the algorithm is going to be terminated, however, if it finds a better neighbor of it, right? So unless it finds the better neighbor, you can choose it, right? But however, there may be a global maxima also, which is going to have the higher objective function. Next is ridge. What is ridge means? When it occurs in multiple peak values of the highest value, right? So there can occur a multiple local maxima. So there comes a problem which to be chosen. And plateau is where I said all the neighboring value of the objective function is going to be same, which is nothing but the flat, is nothing but the plateau. So it is very hard to find in which path to be chosen, right? So these are some of the problems in hill climbing, right? So here is an example for calling the hill climbing, right? So just like climbing the Everest in a thick fog with amnesia. So this is very good example. What we talk about is, you know about the amnesia patients, how they will remember that too while climbing the hill, right? We have to remember the path where we start and where we reach. There can be ups and downs also, right? But among all these, you have to choose a wiser path to reach it, right? So that is where it is given, right? So coming to the algorithm, if you observe the algorithm, we use a function name which is a hill climbing, right? So hill climbing is going to return a state that is local maxima. As I told you, instead of considering the highest objective function of global maxima or minima, if there access multiple global maxima also, we could choose a best from that, right? So we will return a state if it has a local maxima, right? And what is the input is a given problem. We will use two variables. One is to represent what is the current state and what is the neighboring state. So from the current state only the solution is going to be chosen, right? So that we need a two variables, which is current and its neighboring node. We have to compare to the neighboring node and choose the best one, right? So now here, at the initial state when the problem is being assigned, the node is being taken and consider that as the current node, right? So which is nothing but the first state of it, right? And then from that you have to make a loop of it to find its neighboring node. How do you find the neighboring node? When you explore the node from the current state, right? So if you observe here the neighboring node, the highest valued successor of a current node, which is being a neighbor node. So if you find it, right, check whether if value of neighbor is less than or equal to value of current. You have to compare the neighboring value with the current state. Then return the state which is going to be current and make that current state as the that neighboring state as the current state, which means that state is going to be the current state, and from current state the further state will be derived till it reaches to the goal, right? So this is a simple algorithm which talks about how the hill climbing compares the neighbor node, and the neighbor node will be, after chosen, that becomes a current node, right? So we have types of hill climbing, right? So one is simple hill climbing, which we talk about now. It is a simple hill climbing. Then we have the steepest ascent, right? And then we have the stochastic hill climbing. So actually, to overcome the problem with the hill climbing, we have this other types, right? So where it much concentrate on the local maxima, right? So what is steepest ascent is going to be the advanced form of your hill climbing, right? A simple hill climbing. And what is the main goal of it is, it is going to go through all the neighboring nodes and select the node which is nearest, which will lead to you to the goal state, right? And it is going to be more computational power than simple hill climbing what we talk about, yes, because it has to search with the multiple neighboring nodes, right? Next is your stochastic. So stochastic hill climbing where the neighboring node checks it's better than the current node instead, right? And we know that which is going to be the least node, that could be the path where we choose it, right? But stochastic is going to choose a random path. So it explores further, right, based on the previous decision. It predefines whether to go to the neighboring node which has the node which has the highest or the least. It doesn't matter, but stochastic is going to blindly follows any one, take any one path randomly, and it is going to explore further, right? So next class we'll see about CSP.